All right, in this video, I'm talking about L'Hopital's rule. And I'm just going to start by telling you the theorem. If the limit of f of x is 0 and the limit of g of x is 0 at the same place, and we're looking at the limit of their ratio, which is going to 0 over 0, we can take that limit by considering the limit as x approaches c of f prime of x divided by g prime of x. Okay, so what we're doing is we're taking the derivative of the top and the bottom. We are not using the quotient rule. We're plugging in for x and hope that we're not getting 0 over 0 or infinity over infinity. That's another case that we can use L'Hopital's rule. And then we're repeating if necessary. All right, so let's jump in on some examples. So always your first recourse when encountered with a limit problem is to just plug in. So I'm going to plug in x equals 0, and I'm going to get e to the 0 minus 1 is 1 minus 1 over 1 minus 1. Okay, this is really important. You need to show that the limit goes to 0 over 0 or infinity over infinity. Then you're going to call on the authority of L'Hopital or state what the rule says. Okay, so I'm going to say use L'Hopital's rule. On some free response questions on the AP exam, really depending on the year and the type of question and how people are scoring, not showing that it goes to 0 over 0 and not stating that you're using L'Hopital's rule can lead you to not getting the point even if you get the correct answer. So it's really important that we justify our work here. Okay, so that's going to be equal now to the limit as x approaches 0 of, okay, I'm going to take the derivative of the top. The derivative of e to the 2x is 2e to the 2x. The derivative of the bottom is e to the x. And now I'm going to plug in again and see what I get. And I'm going to get 2 times 1 divided by 1, and that's 2. Okay, this one is one that maybe last year we solved by multiplying by the radical conjugate. And that still works. You're going to get the same thing. But what I'm going to do instead is I'm going to use L'Hopital's rule. So I'm going to start by plugging in x equals 0. And I'm going to get the square root of 4 minus 2 over 0, which is 0 over 0. So I'm going to use L'Hopital's rule. And I'm going to say that this is equal to the limit as x approaches 0 of 1/2 of 4 minus x to the negative 1/2. Then multiply by the derivative of the inside is negative 1. Divide by 1. Okay, and then I'm going to plug in x equals 0. Okay, so that's going to be half of 4 to the negative 1/2 multiplied by negative 1. And 4 to the negative 1/2, I'm going to take the square root of 4 for the 1/2 power, and that's 2. And then I'm going to take the negative 1 power of that, so that's going to turn it into 1/2. So I've got half of half is a fourth times negative 1 is negative 1/4. And that's what you would find if you multiplied by the square root of 4 minus x plus 2 over the square root of 4 minus x plus 2. All right, this one, at the beginning of the year, we were saying that this is a derivative question in disguise, right? We're saying that this is actually the derivative of, okay, if we make this x minus 0, this is the derivative of sine of pi over 3 plus x at the point where x equals 0. But though that was kind of hard to keep everything straight, and I really didn't stress that very much, and I only gave you one question on the test, and it was a really obvious one. And the reason why is because we're coming back through now with L'Hopital's rule to make this much, much easier. Okay, so what I'm going to do is I'm going to plug in, and this is going to equal sine of pi over 3 minus the sine of pi over 3 divided by 0. Okay, well that's 0 over 0, so I am going to need to use L'Hopital's rule. By the way, what is the sine of pi over 3? Yeah, it's root 3 over 2. Okay, you got to think about that for a second. It's up towards the top, and sine is the y value, so that's pretty big. Pretty big is root 3 over 2. All right, so since that goes to 0 over 0, I'm going to use L'Hopital's rule. And that's going to be equal to the limit as x approaches 0 of cosine of pi over 3 plus x. Sine of pi over 3 is just some number. So when I take the derivative of some number, I'm going to get 0 over the derivative of x is 1. And I plug in 0. And so that's going to be cosine of pi over 3. And then I think to myself, okay, I'm going back over here. That's pi over 3. Cosine's the x-coordinate. I didn't go very far over. Not very far over is 1/2, yeah. Okay, so this is equal to 1/2. Which is also the derivative of sine of pi over 3 plus x at x equals 0. And you can check that if you like. Okay, the next one I've got is the limit as x approaches 0 of sine x over x. And in most calculus courses, that would be one of the things at the beginning that you would be kind of just asked to memorize, this limit. It's a very common trig limit. It's how we would prove that the derivative of sine is cosine. And so maybe next time I get y'all for that hour after lunch, I'll go through and do a bunch of proofs now that we have our trig limits and the ability to use L'Hopital's rule. But what we're going to do is we're going to say this goes to 0 over 0. So we're going to use L'Hopital's rule. And I'm going to say that that's equal to the limit as x approaches 0 of the derivative of sine divided by the derivative of 1. And that's 1 over 1 is 1. Okay, so the limit of sine x over x as x goes to 0 is 1. But you don't have to know that because you know L'Hopital's rule now. There's another trig limit that you would generally be expected to memorize at the beginning of a calculus course, but we just kind of saved that in order to get through it quickly so we can cover all the material we got to cover around a block schedule, really. So this is going to 1 minus the cosine of 1 is 0 over 0. So I'm going to use L'Hopital's rule. This time I use the macron. And I'm going to take the derivative of the top and the derivative of the bottom. I'm not going to use the quotient rule. So that's 0 minus negative sine, so that's plus sine x over 1. So that's the sine of 0 is 0 over 1. And that one's 0. Okay, I think I mentioned earlier that we can use L'Hopital's rule for limits that go to infinity over infinity. So if we look at this, and we don't just immediately remember our relative growth rate rules, we can figure out which one's going to grow faster and what the limit's going to be as x approaches infinity. Okay, well, if you know that either x is bigger, you know that it's bigger on bottom and it's going to go to 0. But maybe you forgot, or maybe, it's April and it's been 6 months or 8 months since you did a bunch of limits, and you need to do L'Hopital's rule. That's fine. This is going to infinity over infinity. So I can say that equals infinity over infinity, 490. Can't do that. Infinity over infinity is certainly not a real number. Okay. So I'm going to use L'Hopital's rule. This is going to be equal to the limit as x approaches infinity of 4x to the third plus 2 over e to the x. It's like, oh, that's going to infinity over infinity again. And so you can, again, use L'Hopital's rule. And then you would get 12x squared over e to the x. But again, that would go to infinity over infinity. So you kind of just, eventually simulate a bunch of derivatives. Yeah. And you just imagine in your head, and yeah, thanks to always that one guy that's a little ahead of me in class, they told me yesterday, I think it's, no, wait, this is a different example. Yesterday it was 120, but this one is not going to be 120. What is this one going to be? 48, sure, I believe you. 48 over e to the x, and we know that number over e to the x is growing really fast. 48 is not growing at all. This is going to have a huge denominator, and so that limit is equal to 0. Okay, now, there's really no substitute for just knowing that e to the x grows faster than any polynomial as far as solving problems quickly, but this is a good reason why e to the x grows faster than any polynomial, if you think about it. Okay, they're telling me now that 48 was a lie. It was actually 24, but I'm not going to go back and fix it. The point is, it was a constant, and e to the x was not a constant, and it grew. And so the denominator was really huge, and therefore the fraction was 0. All right, over here. we have something going to infinity over, what happens to log of x as x gets really large? Oh, descent. So we think, remember that log of x is the special exponent that we put onto e to get x. Okay. So if we're thinking about what exponent do I have to put on e to get a really huge number like infinity, you have to put a really huge exponent on it. So that's why log grows, it goes to infinity. Now it goes really slowly, but this goes to infinity over infinity. So I'm going to use L'Hopital's rule. Okay. And then I'm going to say that this is equal to the limit as x goes to infinity of the derivative of 5x to the 4 is 20x to the 3. It's the derivative of log x, 1 over x, yes, which is now the limit as x goes to infinity of 20x to the 4, and that is going to infinity. So in this case, infinity over infinity, I don't say equals, but was infinity. And I think that's going to be all. There's plenty of L'Hopital rule practice out there. So if you feel like you need more practice with L'Hopital's rule, I would recommend a quick Google or YouTube search.